What's up guys, it's me Sir Ernest, and today we're going to continue our discussion on Newton's laws of motion, and in this time we're going to relate this laws of motion to linear momentum. Now we already know that linear momentum is just the product between the mass of the particle and its velocity. We usually write this as small letter p, and it is a vector quantity. Defined as a product of the mass, which is a scalar quantity, and the velocity, which is a vector quantity. So for example, if this is your mass m, and let's say the velocity of this mass is directed in this direction, using rules of vector algebra, we can see that the momentum of the particle p would follow the direction of your velocity because m is always positive. So in this case, the momentum or linear momentum will be directed in that direction. Now, as I mentioned also earlier, Newton's second law of motion can be rewritten in terms of the linear momentum. So in this case, the net force acting on the particle, or simply F, is now equal to the time rate of change of the linear momentum with respect to time. Using this definition, this is derivative of m times v with respect to time. Now, this is not the familiar form of Newton's law, but however, this law or this equation is actually a more general form of Newton's second law, since it also considers a particle whose mass changes during the motion. So for example, rocket motion. Now, because mass may also be a function of time, and velocity may also be a function of time, therefore this derivative will result into two terms. The first term will be the usual form wherein your mass is multiplied with the acceleration. But since here the mass is not necessary, the mass is not constant in time, so therefore we must also consider how the mass changes with time. So the second term will now become the rate of change of the mass as the mass undergoes motion times the velocity itself. Okay? So as you will notice that for constant masses, that means the derivative of the mass with respect to time is equal to 0. So this equation will now become the usual f equals the m times the derivative of the velocity with respect to time. Now, consider from the third law of motion, let's say we now have two mutually interacting particles of masses m1 and m2. And let's say, for example, the forces are attractive in nature. So this force is exerted on m1 by m2. So let's call this f1. And this force is exerted by m1 on m2. So let's call this f2. Okay, so by Newton's second law, f1 will be equal to the derivative of the momentum of particle 1 with respect to time, while force exerted on 2 will just be equal to the rate of change of the momentum of particle 2 with respect to time. Now, Newton's third law says that F1 is equal to negative F2, assuming that the two forces are central. So by virtue of Newton's second law, this will now be equal to derivative of the momentum of the first particle with respect to time, and this is equal to the negative of the change of momentum with respect to time of the second particle. Now rearranging this, now have derivative of momentum 1 with respect to time plus derivative of momentum 2 with respect to time, and this is equal to 0, or the total derivative with respect to time of P1 plus P2 is equal to 0. So what does it mean? It means that the sum of the momentum of particle 1 and particle 2 is a constant. So this tells us that Newton's third law of motion implies that the total linear momentum of two mutually interacting particles is a constant. So this constancy is a special case of a more general situation in which the total linear momentum of an isolated system, so when we say an isolated system, we mean a system subject to no external net force, is a conserved quantity. So this equation is what we call the law of conservation of linear momentum. Okay, so again, as long this is applicable as long as the system of these two particles is isolated. Okay, so that relates Newton's laws of motion with linear momentum. And I hope you learned something today, and I'll see you guys in the next video. Bye bye.